Okay, so apologies for the very dull linear algebra review, but I thought it would be useful, especially when we get onto the later topics in the course. Okay, so just a summary of what we covered last class. We did linear regression, so the first learning algorithm was using regression, but using just a single feature. So just using one feature, so for example, tumor size or the square footage of a house, and then you want to predict the outcome given that feature. Okay, so we only used one feature and found a line of best fit suiting these points using the gradient descent algorithm, all right? If you recall the algorithm, the model, the prediction model is just using basic slope and intercept model. So this is the intercept, and then this would be the slope, okay? And the algorithm is first you initialize so what you're doing is you're trying to find the parameters theta 0 and theta 1 to best fit the line, best fit the points through the best line of fit. So you initialize, it's an iterative algorithm, so you start with an initial point, so in this case you can make them both 0 if you wish, and then you have to repeat the following until convergence. So you simultaneously update the parameters using these, this equation. So you take your theta 0, and then this is the step size here. So alpha is the step size. It tells you how much of a step you need to go in the direction of where the minimum is of your cost function. And then here, all you're doing is you are applying the prediction model, and then you're taking the sum of differences between the expected outputs and the actual prediction values, and then you're averaging them all up. So that would be for the intercept term, and the slope term is you're doing exactly the same thing, but you're doing you have a factor of x there as well. So this is just summarizing from last class. All right. So let me just scroll down here so you can see that. Okay. So usually in practice, you just don't use one feature. One feature is not enough to give you enough, accuracy. So you probably want to incorporate more features, more than one. So you don't want to use, for example, in the housing prices, you don't want to use just square footage. You might want to use such examples as how many bedrooms there are. Is there a pool, location to the nearest school, other features that will be used to better predict the price of a house. All right? So let's see here. So for example, okay, we had housing prices. Okay? So this is what we had before. Before we just had one feature to help us discriminate between different instances in your training data set. So, in the thousands. Let me just scroll down here. Okay. So then in that case we had 2104, 1416, and then this is 1534, 832, and so on. All right. And then the square footage was 460, 232, and then 315, 178, and so on. Okay, this is just having one feature, and we have that. So this is example. So for better accuracy, we need more features. Just one feature is enough. You probably want to use maybe 2 or 3 to help you, get a more accurate prediction algorithm. All right. So it might look like this, or you have multiple features. So something like this may work. So you have, not only do you have the size and square footage, right, but you also might have, a number of bedrooms, right? You might also have the number of floors. If you have just a bungalow, or if you have, 2 or 3 floors, that also factors into the price as well. It's not just square footage, right? Because if you had, let's say, a 3,000 square foot bungalow, it's probably not as cost effective if you were to have a 3,000 square foot house that has 3 floors. The pricing is obviously going to be different. You also might have to consider the age, right? The age of the home. This is in years. Obviously, the older the house, it depends on how much maintenance you put into it, but usually the price either increases a little bit because it's it's established. And finally, you have price, which is in the thousands. So you might have something like this instead. Okay, so this is 2104, and this is 1530, or not 15. What was it? 1416, 1534, and then this is 852, and so on, or 832. Right, and then you might have 5 bedrooms here, 3, 2, 1. Right, the number of floors you might have, 1, 2, 2, 1, something like this. These are just random numbers I threw out. I've never heard of a house that had 5 bedrooms and 1 floor. That's a little unheard of. But yeah, I just threw in random numbers. I probably should have double checked these before I put them up. So, and then we have 460, 232, 315, and 178, and so on. See, when you have more features, it paints a better picture of what's actually going on, right? So just using square footage by itself is not enough to figure out what justifies the price of a house, right? So square footage, so let me see here. Square footage, square feet is probably not the best performance-wise. You got to add more stuff if you want to, have a little bit of a chance getting better accuracy. Okay? There are other factors too, such as below. Because when you're trying to buy property, there are many things to consider, not just square footage. There's other factors that you have to consider, and these are just a sample of what you might want to consider when you buy a house. Right? These are other factors to determine price. All right? Sorry. Okay, so I'm going to just cover a little bit of notation before we proceed, because this notation is important when we actually get on to actually how we would do this for multivariate or multiple variables. Okay, so notation. Okay, just like before, M is the number of training examples, just like from the last class. Okay, so if your training data set consists of 10, then M would be equal to 10. So this is the number of training examples you're using to predict your model, to help you create your prediction model. Now, there's another term which we'll use as N, and N will be the total number of features. So if you remember from just single variable linear regression, N would be equal to 1. It's just the number of features you're considering when you're creating a prediction model. All right, so this is the number of features. Okay? And then what I'm going to do is I'm going to use X subscript K. This is what is known as the kth feature. Okay, so for example, if you go back to our table, there's 4 features in total. So this would be X1, X2, X3, and X4, right? So starting from left to right, so the subscript tells you what feature you're looking at. So X1 would be the feature that is representing the square footage, or X03 would represent the number of floors that are in the house that you're looking at. Okay, so X sub K is the kth feature in your data set. Okay, now X power I, as we talked about, this is not to be confused with the power I, it's the ith training example. The ith training example that consists of n features. Okay, so for example, if we take a look up here, this entire row here, this here, everything is X1, all right? And then, for example, this whole thing here will be X3, all right? So each training example consists of multiple features. So you have X1, X2, and so on, and then X would be the actual, example, all right? A couple more. Now we're going to actually get onto the nitty-gritty here. So this here is very important. So X sub J I. So what does this mean? This means that for the ith training example, you want the jth feature. All right? So the jth feature for example I. Okay? So if you take a look above, this here, for example, okay, this is the 4th training example. So the examples are vertically, okay? So this is the 4th row, this is the 4th training example, and this is feature number 2. Sorry, it's X4, and then feature number 2. Okay? So it's the 2nd feature, the 4th training example. All right, let me just do another one. This case here, this will be the 3rd example, and then this is the 3rd feature. All right? Or if I did this one, this is the 1st example and the 4th feature. So the subscript tells you what feature you're looking at, and the superscript tells you what example you're looking at. Okay, so xj power I is the jth feature for the ith training example. Finally, just to be sure, this would be x1, 4. Okay, so subscript is feature, superscript is example. Okay? And then finally, yi is the expected output. For each xi. All right, so I forgot to do that, and this is over here. This is y, right? So in this case, this is. Yeah. Oh, yeah, my bad. Just making sure you're paying attention. All right, so this is 1, 4, right? Thank you. Sorry. I just had that before. Yeah. 1, 4. Yeah, making sure you're paying attention twice. All right? Okay, so this is y1, this is y2. All right, this is y4. All right, the rest of it is good. So you have the second feature, fourth example, third feature, third example. Okay, we're good. Thank you. Okay, so that's just a little bit of notation before I proceed. Okay, we're okay so far? All right, fantastic. Okay, so before you just had a simple linear, just one variable model. So this is the old hypothesis, right? This is the old hypothesis. This is just okay. So the new hypothesis, it's just you're extending this into n weights. So this is, we're not using this anymore, okay? What's going to happen is that you're going to use this term now. So it's just, you're just adding more stuff on top of the sum. This is the new hypothesis now, okay? So basically the new hypothesis, it's just a weighted sum of features. So for each example, you have n features. So what you're doing is you're taking each of these features, you're putting into this hypothesis, you're weighting each feature by a certain amount, and then you add everything all together, okay? So this is what the new hypothesis would be. So this here is the old one. This is the old one, right? And then this whole thing is the new one. Okay? So in this case, there's 4 of them. So for the housing prices, there's 4 features, right? So we have, this is, oh, sorry. Let me just move it over here. Oops, cannot write. Okay, so remember this is square footage, right? This was the one, let me see, number of bedrooms. This is number of floors, right? And then this was age. Okay, so it's just a weighted sum of things now. So what we're gonna do, proceeding from here on, is we're gonna represent this as vectors, right? So you can think of computing your hypothesis as being a dot product between the vector x, which is which is the example that you're looking at, and the parameters that you want. Okay, so both x and theta can be column vectors, and computing the hypothesis is just a dot product. Okay, so for example, if x was this, now this is x. Well, you can think of this as 1, right? And theta is, and you just compute the dot product, right? That's why the linear algebra stuff was, I had to push it because it's very, you need to know this when we get to later on in the course. Okay, so this is x0. It's usually 1 for a convention. All right, to enable for you to in order to get the bias in. All right, so and therefore the prediction is just theta transpose and then x. Okay, so that's how you compute it. And then you can. This also generalizes to single variable too. It would just be a 1/2 with a 2/1, and then you can do a dot product that way. Okay, so let me just summarize. So predicted output is a weighted sum of features, like for example x1, x2, all the way up to xn, right? And okay, with parameters, I guess. All right? So you can represent it as a dot product. That's good. Okay, so now that we have multiple features, so we only dealt with gradient descent for one variable or one feature. So now that we have multiple features, how does that affect our algorithm? So we can obviously extend this algorithm to multiple features, but how does it actually affect it? Right? So how does this affect gradient descent? Not that much, because before, if you take a look at gradient descent, there was only two parameters we took a look at. It was the slope and the intercept. So if you want to do it for multiple features, you just do gradient descent for as many features as you have. So if you have 4 features, you just do it for theta 0, theta 1, all the way up to theta 4. So you're just repeating the same procedure, but for as many features that you have. All right? So how does this affect gradient descent? All right. How does this affect gradient descent for finding the best parameters? Sorry. All right. Okay. So how does this affect us? So let's actually go a little deeper. Okay. So if you remember, this is the cost function from before. This was only dealing with 2 variables. Cost function from before. Okay, so it was just 2 parameters, theta 0 and theta 1. This is the mean squared error, right? And you have to square the differences because it makes the cost function convex. If you don't do that, then it's non-convex and you won't get a unique minimum. So that's the whole reason why you square it. Okay, so this is from before. Now the new cost function is very simple. You're just adding more parameters to it. So instead of just theta 0, theta 1, you're adding more. So from theta 0 all the way up to theta n, right? Oops, new cost function. So, all right. So there's n features now. So we have 1 over. Still the same thing, but we can expand this now to incorporate multiple features. Oh, sorry, this is a squared. I got the squared there. Okay, great. And then this can expand to what? It's just the weighted sum as we talked about before, right? Actually, what I'm going to do is I'm going to change this, so I'll represent this with capital theta, all right, to represent that vector parameters, okay? So this is 1 over 2m. This expands to what? So we have theta 0 plus theta 1 x1 plus theta 2 x2, all the way up to the end, right? And then subtract this. Actually, this is the ith training example, right? And then this is with the predicted output. And there we go. Okay, that is good. Just double checking. All right. So this is what it was before. So this is what the hypothesis would be. So this is the new one. Okay, so how do we adapt this to gradient descent? So if you recall, it's not that much of a stretch actually. It's actually, it's just additional steps you have to do. So repeat. So it was theta j, you update this with okay, for j equals, let's see, 0, 1, all the way up to n. Okay, and you also have to simultaneously update as we talked about before. So what simultaneously update means is that whenever you update each parameter, you don't use those updates to compute the rest of the parameters. You have to set those aside, and then you use those for the next iteration. All right, so that's what simultaneously update means. Okay. So that's what the gradient descent was. It's good. So, you know, but the problem is this person over here. So how would we compute that term? How do we compute the partial derivative of the gradient with respect to theta j? How do we do that? So okay. So just like from last class, let's break it down. All right. So we're going to just write out the cost again, and then we're just going to take the derivative of that. Right? So okay, let me just copy from the above here. Just gonna, where is it? Okay, great. I'm just gonna take this guy and copy it. Nice. Okay, so let me just put it here. Save me some time. Where's it? Here we go. And here. Yeah, good. So I'll just get rid of this. Okay, so this is what happened before. Okay, so I need to take the derivative of this, right? Okay, so actually let me just expand it a little bit before I proceed. So 1 over 2m. So I got to do this for the first example. So this is theta 0 plus theta 1, x1, 1, x2, 1, and so on. Right? Minus. Okay, so that's the first term. I'm just expanding this out, okay? So plus 1 x1, 2, theta 2, x2, 2. Keep going, and then the last one, second example. Okay, and then you just keep going until the very end. x1n, or sorry, m, because there's m training examples, right? 2, x2m, and then so on and so forth. Great, all right? Oops, n. I seem to get my subscripts confused. Okay. All right, so that's how it is expanded. So what we need to do here is we need to compute the partial derivative with respect to theta j. All right, we have to do it for every single parameter. Okay, so how do we do this? So you have 1 over 2m on the outside. That's perfectly fine. Okay, so for each of these terms in the sum, you have to compute the derivative with respect to theta j. So how do you do that? So you have to do chain rule, right? So the 2 goes in the front. So you have 2 here, and then you write out everything that's inside the bracket. Okay? And then you have to multiply with the derivative of the inside. So remember, you're differentiating with respect to theta j. So this whole, everything inside the bracket, you can treat as a constant except for the theta j that you're looking at. So when you're differentiating, you know, this all goes away, except for what? When theta j, for the theta j term. When you differentiate with theta j, it's just 1, and then the output is just x of j, right? So in this case, you just get x, j, 1. Right, so it's a sum of weights. So you have theta 0 plus theta 1 x1, and then you keep going, and then when you differentiate, everything goes away except for the constant that deals with theta j. So when you differentiate with respect to theta j, it's 1 times xj in whatever example we're looking at there. And that's what happens there. Okay? And then you just repeat it for the rest of it. Oops, this is the second example. Okay, and this is the second feature, and then so on and so forth, all right? I won't bore you with the details there. So now these twos cancel, all right? And then finally what you get is just a summation of all these terms. It'll be 1 over m, and then summation from, let's see here. Oops. And then multiply by x, j, I. Pretty sure. Okay? And that is it. Okay, and then the accepted convention is the following. So now that's pretty much what the gradient term will be. So for each feature that you have to compute the sum. So you're taking the sum of differences between the current predicted, with the prediction models, the prediction with the model, subtract that with what the true output would be, and then you take those differences and then you have to multiply it with the jth feature that corresponds to theta j for every example that you have. All right? So I'll do a little bit of an example in a little bit. So therefore, the new algorithm is this. So instead of just doing it for 2 features, just theta 0 and theta 1, you're doing it for as many features as you have, and you're also including the bias term as well. So theta 0 is theta 0 minus, and then you have alpha. Yeah. Okay. And then theta 0i. Okay. And then you do the same thing for the other stuff. So I'm just going to take this and copy it. Where's my right click? There we go. Okay, I'm going to move this down. Okay, change this. Theta 1, change this to 1. And then you keep going down until the end. We just write it. Let me just fit it down here. Okay, I won't copy and paste this time because it's too small, so that's okay. So theta 0, xi, not theta 0, sorry, just theta by itself. And then x and I. Okay? And then usually we let this be 1. So this is actually 1. X0 is 1 to allow for the bias term. Okay, so usually we let this be 1 to represent the hypothesis, right? Because you're doing a weighted sum. So we usually let this be 1. So you pretty much do everything, but you let that be 1 instead. Okay. All right, so why is this useful? There's two ways to approach this gradient descent with multiple variables. You can do it using the for loop approach, or what you can do is just, you can modify the linear regression code. So instead of just calculating theta 0 and theta 1 statically, you just loop through every single parameter and compute the update that way. You can do it that way if you want, especially if you have large data sets, but I'm going to show you how to do it with linear algebra, and it's actually quite elegant. All right? So, and then you'll see that the equation is simplified a lot. So here's from a linear algebra viewpoint. Okay? So recall placing training examples in a matrix, not D, sorry, in a matrix. We'll call this X. Okay? And then each column is a feature. Let me just scroll up so you guys can keep copying that here. Each column is a feature. Okay? And each row is an example. Okay, that's great. So, and then you got to remember to add a column of 1. So add a column of 1s before the examples. Okay, so it looks something like this. So you have x, and then this is equal to, right? And then we have, let's see here, x1, 1, x2, 1, and so on, right? So each row represents a training example, and each column represents a feature, right? All right. And then you can generalize this. You can keep going on, keep going on. This would be the M training example for the first feature. Sorry. Keep mixing up my notation. This is x1, m, x2, m, and so on. Okay? So this is the matrix that you'd represent in memory, assuming that, if you have maybe 1,000 examples, that's all right. That's no problem. You can represent that in memory. Okay? And then what you could do is represent parameters as a vector, a column vector, all right? And it's n by 1, okay, because you have to incorporate the bias term, so it's n plus 1 by 1, right? This is for theta 0. So what I mean is, capital H like that. So this is theta 0, theta 1, all the way up to theta n. Okay, so this is n by 1 rows. All right, so accommodate for the intercept term. Okay, and then you can also represent the expected output as a vector as well. Okay, represent expected output. So this is represent expected output as a vector too. Okay, so y equals, this is y1, y2, and then all the way on to y of m. Okay, that's good. Okay, so let's start slowly here. Okay, so we've got this. So you have your matrix of points. You add a column of ones, and then you also have your vector of parameters. Okay, and then you also have your vector of expected outputs for each example. Okay, so let me just recall the gradient term. So it was this guy right here. So from 1 to m, and then okay, and then this was x, j, I. Okay, if you remember the review, you can represent this as a dot product, right? So this you can represent as a dot product between the parameters and each training example, right? So we can represent as a dot product. Okay, that's cool. All right. So remember, how is that useful? So remember, if you had the data matrix on the left, and if you multiplied with a vector of parameters, you're computing the hypothesis or the predicted values for every single training example in your data set. All right? So we can compute our predictions for each example using matrix vector multiplication like we did before. Okay? So x times theta. All right? So in this case, you can represent each of these as a, as a row of examples. So this would be x1. And then I need to transpose this because, actually, no, it's okay. So actually, it's okay. We'll do that. This is fine. All right? Okay? And then if you multiply this by your vector, so this is theta 0, theta 1, all the way down to theta n. Okay? So this is just computing the dot product, right? So this becomes, let's see here, so this is just, if you did this, it would be what? Theta, let's see, transpose times x1, x2, and so on, right? Actually, no, sorry. Let me just do this. It would be, let me just get this notation right. And so on and so forth. Okay? And then the dot product is also commutative, so you can do theta transpose and then x if you wish. And so on and so forth. Something like that, I guess. Okay. Okay, anyway. But the point is that you're representing everything as a dot product here. Okay, that's nice. So what is this exactly doing? What it's doing here is that it is computing, sorry, where am I going? All right, sorry. Okay, where am I going with this? All right. So this computes the predictions for every single example that we have. Now, if we decided to take this output and subtract this with your predicted or the expected predictions y, what you're doing is you're actually computing the difference between the predictions and the expected output, which is useful, and I'll show you why in a minute. So we can also compute the difference between the predicted and expected outputs for each example. Okay, that's good. All right, so if I did x theta minus y, okay, this would be equal to what? Right, and then this is okay. And remember, this is just h theta of x1, right? So in this case, this vector is also equal to so this is good. So what you're actually doing here is you're actually computing a vector where each element is the difference between the prediction for your example that you're looking at with the expected output. And then all the way to the end. Great. Okay, this is good. This is good. Okay, so why is this useful? Well, I'm building up to that point. So let's see. So suppose we transpose X. So if we decided to transpose X, what's going to happen is all the rows become columns and all the columns become rows, right? So what's going to happen here is you'll have a row of ones, right? And then what's going to happen is that each feature is now a row and each column is an example. So 1, okay, and then, sorry, nope, yeah, this is good, X1, sorry, just double checking. Yeah, sorry, my bad. This is X1, 2. Okay. X2, 2, all the way down to Xn2, and all the way down to Xnm. Okay. So now we do this. So if you were to take this matrix, okay, so if we computed X transpose X theta minus Y, what would this compute? What does this compute? What this would actually compute would be the gradient term for each example that you have. Okay, so what does this compute? Okay, well, I'm going to show you that. So this, what it does is that this computes update for each parameter simultaneously. And I'll show you why. Okay, because if you remember, X theta Y minus Y was this guy right here. It was the predictions, it was the difference between the predictions and the expected output for each example that you have. Okay? Okay. So let me just do this over here. So if I decide to multiply this by the transpose, let me just take this guy and copy and paste. Okay, copy. And here, paste. Okay. So remember, in matrix, so this is a vector, all right? And this is a matrix. So remember, matrix vector multiplication, what you're doing is you're computing dot products between each row of the matrix with the vector itself. So if you take a look, so let's do the first parameter. Okay, so what's happening here is that you're taking this row and you're computing this with the dot product of that. So what this is computing is just the summation. Actually, we should scale this by m, all right? And this would be, if you actually look hard enough, that's what it's computing. Right, so this is the first parameter, this is the output. So remember, you're taking this row of ones and you're doing it with the dot product of that column. And what's actually happening is that you're summing over all of these differences. And then when you scale by 1 over m, you're exactly computing the update for that parameter. Okay? And then if you decide to do it for the next one, okay, you have 1 over m, and then what's happening here? So you're summing, you're taking this, and then you're summing, you're doing a dot product with that. So you're doing this times the first feature, first example. This times the first feature, second example. So this is actually computing. So, sorry, this is h theta. Okay, and then xj. I. Sorry, not j, 1. Okay, and then you can see a pattern from there. So this formula here actually does it in a linear algebra point of view. So it does it very nicely. Okay, so therefore, gradient descent by linear algebra is simply this. Linear algebra. Okay, so it's simply repeat. Okay, and then what you're doing is theta j. So you're doing theta j minus Well, it's just a vector, so we'll just do that. Okay, and that's it. There you go. So instead of looping through every single element or whatever, you would just compute this by itself. And this is the matrix where you're appending the column of ones before. So you take the transpose, then you multiply that with x times theta minus y. So this is an n plus 1 by 1 vector. Okay. This is m by 1 vector. Okay. And this is m by n plus 1 matrix. Okay. And that's how you compute it by linear algebra. So instead of looping through every single element or whatever, you can compute it by linear algebra instead. And this will do it very nicely. So this is actually what you're expected to code in the lab. So all you have to do is just follow this formula if you wish. Or if you want to do it by looping, whatever you're comfortable with, but that's fine. But I find that this is much easier to look at. So all you have to do is just compute this in MATLAB, and you loop for as many iterations as you have, and then you update. And this is nice because when you're doing matrix vector multiplication, you're doing that simultaneous update. You're not actually using any of the parameters from that update, and you're factoring it into the parameters for the current iteration. So it's actually very nice. All right? Okay. Yeah. All right. And then one last, so this is, it's good. Parameter. Okay, let me just throw this stuff in. So we've got theta. So this is the vector of parameters. Let me just double check how much stuff I got. 1, let's see, 2, 3. Okay. Okay, so vector of parameters. So this goes from theta 0, theta 1. Okay, X is the data matrix. All right, so it was this stuff here. Just copy this. Where is it? Okay, I'm not going to put it here, obviously. I'm going to put it here instead. Right, and that's it. Okay, good. So this is data matrix. Okay, and y would be the expected output as a vector. Okay, and this is y1, y2, and so on. Okay. So then finally, you can also compute the cost function using a matrix vector multiplication if you wish. So if you actually do this, can be computed by linear algebra. So I won't prove it, but I'll show you. So it's basically just this. It's j, and then you have 1 over 2. And then remember, what you're doing is you're taking the predictions subtracted with the expected output and you're squaring them. So if you remember, you can just do that by dot product. So in this case, you would just do this. Okay? So this is actually easier to do. So you don't actually have to loop over every example. You would just compute it this way. Okay, because what's happening here is that it gives you a vector of expected, the differences, and then if you transpose this with itself, it gives you the sum of squared, sum of squares, and that's what you get. Okay. I'll just give you a little prelude to what we're doing, then I'll take another break, and then we'll come back and talk a little more. All right, so, okay, but any questions here so far? Are we good? Yes? Yeah. No, we prepend because when you're doing the dot product between the feature vector, you also have the theta 0 term. So you have 1 times theta 0, and then plus theta 1 times x1, and down to theta n. So you have the 1 there because you just want the bias, the theta 0 term, to be by itself. You don't have a feature there. You have just a column of 1s. So you have 1, and then your features, and then dot product with theta 0 with your parameters. So when you do the dot product with that and this vector, you're computing the hypothesis, the prediction of that particular example. Okay? That's why you prepend the column of 1s.
For smaller data sets, it's more efficient to use the matrix than the group for the computer?
Yep, that's right. With large data sets, you have to do a bunch of SQL queries, so you'll have to loop through them. Okay? So let me just give you a little prelude to what we're going to talk about, then we'll take a little break, and then we'll come back. Ready to send in practice. So what we've talked about so far is if you take a look, each feature by itself has its own different dynamic range. So for example, square footage can vary between 0 and let's say 5,000, for example. Or the number of bedrooms has a smaller range from 0 to 5, right? So each feature by itself has very different dynamic ranges. So a problem with gradient descent is that if you have a feature which is varying dynamically, which has a very wide dynamic range, the algorithm will have a little bit of time trying to find the right parameters because the gradient is motivated by the largest change because of the large dynamic range. So it actually gives you a little bit of a problem when you're trying to get it to converge. So one thing you do is you do something to the features. You normalize them or you pre-process them to make it easier for gradient descent to converge. All right? So usually, I'll just make that note and we'll take another break. Usually each feature has a different dynamic range. Okay? So if you recall the housing prices, okay? You know, the first feature was the square footage, right? And it might vary between, 0 and let's say 5,000, for example, okay? And the second feature was what? It was the number of bedrooms, okay? And that could vary between 0 and 5. So if you take a look here, the range, the dynamic range between each feature varies very widely, okay? So let me just make one more note. We'll take a break here. So let's see. Oh, come on. All right. So the different ranges affect how gradient descent works, or affect how it converges. Affects how gradient descent converges. Descent converges. Right? So the larger the dynamic range, the longer it takes for gradient descent to converge because there's that large variability. All right? So larger the range, the longer it takes to converge in practice. Okay? So when you introduce more features, there's going to be a high chance where some of those features are going to have large variability. So the more features you have, naturally it's going to take longer to converge. Okay? So more features equals more variability. Right? And slow convergence is what is resulting. Okay? So the solution, right, is to, before training, try normalizing each feature. Normalize each feature. All right? Normalize each feature. Okay, so we'll stop there. And then when we come back, I'll continue on. I'll talk about this more after the break.